Good morning, students. In today's lesson, we will see the classification of materials according to their magnetic properties. We will learn the properties of different kinds of materials like diamagnetic, paramagnetic, ferromagnetic, and also we will refer to antiferromagnetism and ferrimagnetism. Then we will focus our attention on ferromagnets, which are strong magnets, and see their properties like magnetic domains existing inside the ferromagnets, then the hysteresis, which is a special property shown by ferromagnets. Then, according to the shape of the hysteresis curve, we will see how ferromagnets themselves are classified as soft magnetic materials, which are used to make temporary magnets, and hard magnetic materials, which are used to make permanent magnets. So let us go ahead and go into the topic. Let me share my screen with you. I hope you can see the screen now. So as I said before, we can classify materials according to their magnetic properties as diamagnetic substances, paramagnetic substances, and ferromagnetic substances. By the end of this lesson, you should be able to draw a table that compares the properties of these three kinds of materials. Then we will also see what are antiferromagnetic substances and ferrimagnetic substances. So, diamagnetic substances. These are substances which gets weakly magnetized opposite to an applied magnetic field, as you can see here. Here there is an applied magnetic field represented by B, and it is directed towards the right. Now, when we place a diamagnetic substance, as you can see here, the magnetic dipoles or small atoms or molecules which are present inside the diamagnet will develop a small magnetic dipole opposite to the direction of the applied magnetic field, as you can see here. So here they will try to oppose the applied magnetic field, or in fact, literally they will push out the magnetic field lines. Here you can see that the number of field lines within the material is less compared to the number of field lines outside, or the number of field lines that existed before we kept the diamagnet. So these are substances which get weakly magnetized opposite to the applied magnetic field, and they are slightly repelled by a magnet. Slightly repelled by a magnet means it is not evident unless the applied magnetic field is very large. If the applied magnetic field is very large, you can see the repulsion of diamagnetic substance. If it is weak, the repulsion is so less or it is negligible, it won't be evident. Now, when we place a diamagnetic substance in a region where the magnetic field is non-uniform, then the diamagnetic substance move from a region of stronger field to a region of weaker field. This is because they are slightly repelled by a strong magnetic field. They don't like to stay in a region where there is stronger magnetic field. They repel the magnetic fields as you field lines, as you can see here. So they move to the region where the magnetic field is weak if it is a non-uniform magnetic field. And the behavior of diamagnetic substance does not depend on temperature. I'm referring this here because for the other two type of materials, paramagnets and ferromagnets, their properties depend on temperature. Now, these are some examples of diamagnets. copper, zinc, bismuth, silver, gold, lead, glass, marble, water, helium, argon, sodium chloride. Some students have a tendency to believe that most of the metals are magnetic in nature. That's not actually true. See, here you can see silver, gold, lead, they are metals. Still, they are not magnetic in nature. They are diamagnetic, means they slightly repel the magnetic field. Now, magnetic susceptibility of a diamagnet is negative. Chi m is less than 0. Can you tell why? We learned that susceptibility is I divided by H, where I is the magnetization produced inside the material and H is the applied magnetic field intensity. So, we know that the magnetization produced inside a diamagnet is opposite or negative to the magnetic intensity applied. So it will, the susceptibility will be negative because I, the magnetization produced inside the diamagnet, will be negative or opposite to the direction of the applied magnetic field. Then relative permeability is less than 1. We know that the relative permeability mu r is equal to permeability within the material divided by permeability in vacuum. So permeability within the material will be less than that in vacuum. Therefore, the relative permeability is less than 1 for diamagnetic substances. So, we have learned diamagnetic substances which are slightly repelled by a magnet and which are weakly magnetized opposite to the applied magnetic field. Now, let us see the properties of other kinds of materials. Here we are discussing paramagnetic substances. Now, paramagnetic substances gets weakly magnetized in the direction of the applied magnetic field. So they gets weakly magnetized. As we saw in diamagnetic substance, the magnetic field lines are pushed away from the body of the magnet. So this is diamagnetic substance. While in a paramagnetic substance, they will slightly attract the magnetic fields into the material. So here you can see the magnetic field lines are denser within the material compared to that outside. So they are weakly magnetized in the direction of the applied magnetic field, or inside the material, the magnetic field becomes greater than the external magnetic field. And they are slightly attracted by a magnet. Again, as I said, as in the case of diamagnet, to be evident, the attraction of a paramagnetic substance to the magnetic field, to be evident, the magnetic field should be very strong because they are only slightly attracted by a magnet. Now, if we keep a paramagnetic substance in a non-uniform magnetic field, it moves from a region of weaker field to a region of stronger field. Why? Because they are slightly attracted by the magnet. So they like to exist in a region where the magnetic field is stronger. So they slightly move towards a region of stronger magnetic field. Here you can see that the properties are just the reverse of that we discussed in a diamagnet. But paramagnetic substance loses magnetism by the rise of temperature. Can you guess why? At a higher temperature, what happens is the magnetic dipole moments, which are originally arranged in random direction, will remain like that. Here you can see a figure that shows what happens inside a paramagnet. So this is the case when there is no external magnetic field applied. Each of the small atom or molecule present inside the material of a paramagnet are small dipoles, and they are oriented in random nature or in haphazard nature. So there is no net magnetism inside the material. Now, when we place them, the paramagnetic material, inside an magnetic field, or when they are placed in the presence of an external magnetic field, the dipoles, these individual molecules, will align themselves in the direction of the magnetic field. As you can see here, the magnetic field is upwards. So each of these individual dipoles get aligned in that direction. Now, when you remove the magnetic field, what happens? When the magnetic field is removed, they again get arranged in haphazard nature. Similarly, when we increase the temperature, then also the magnetic field get mm, distorted because the dipoles get arranged in random nature. So that is why we say that the paramagnetic substances loses magnetism when the temperature rises. Now these are some examples for paramagnetic substances: aluminium, sodium, antimony, platinum, manganese, chromium, liquid oxygen. All these are examples of paramagnetic substances. And the magnetic susceptibility is small but positive. So what is susceptibility? I by H, where I is the intensity of magnetization produced inside the material and H is the intensity of the applied magnetic field. So it is positive and it is small. Chi m is more than 0, which means that the intensity of magnetism produced inside the material will be a small value, and it will be in the direction of the applied magnetic field. That is why it is positive. Now, relative permeability is slightly greater than 1. So, the permeability inside the paramagnetic substance will be slightly more than that in vacuum. That is why the relative permeability is slightly greater than 1. So, paramagnetic substances have magnetic properties opposite to that of a diamagnet. They are magnetic in nature, but not very strong. Now let us see ferromagnetic substances. Ferromagnetic substances, as you can see here, get strongly magnetized in the direction of an applied magnetic field. So here, this is a picture comparing what happens when you place a diamagnetic material, a paramagnetic material, and a ferromagnetic material in a magnetic field. Here you can see that the diamagnetic material slightly pushes the magnetic field lines out of it, so that the density of magnetic field lines inside the material is less than that outside. Here you can see paramagnetic materials slightly attract the magnetic field towards it. Therefore, the magnetic field lines are slightly bent into the material, while the ferromagnetic materials strongly attract the magnetic field lines surrounding it. So here you can see the magnetic field lines are crowded within the material compared to that outside. And here you can see the relative permeability is very much greater than 1, which means the permeability, the magnetic material, that is ferromagnetic material, will permit magnetic field lines much more than in free space or vacuum. And when placed in a magnetic field, the magnetic field inside the ferromagnetic substances becomes much greater than the external magnetic field. That's evident in this figure. Now, if kept in a non-uniform magnetic field, a ferromagnetic substance moves rapidly from a region of weaker field to a region of stronger field because they are strongly attracted by the magnetic field. Now, the magnetic property of ferromagnetic substances also depends upon temperature. When temperature crosses a value called Curie temperature, the ferromagnetic substances loses its magnetic properties. So after a particular temperature called Curie temperature, the ferromagnetic substances are no longer magnetic in nature. So, do you remember where you have heard this name Curie? You have heard this name before because it is the name of a scientist. You must be remembering Marie Curie, who have discovered artificial radioactivity. So this name is given to this particular temperature because it was she who studied the property of ferromagnetic materials at different temperatures. So the Curie temperature of iron is 1043 Kelvin. That's very high temperature. So at very high temperature, the ferromagnetic substance loses its magnetic properties. And for different substances, the Curie temperature will be slightly different. So iron, nickel, cobalt, etc. are examples of ferromagnetic materials. Usually what we call as ferromagnetic substances are ferromagnetic in nature because they are strongly magnetic. Their magnetic property is evident even if the applied magnetic field is weak. Now, the magnetic susceptibility is large and positive as expected because the magnetization produced inside the material is much greater compared to the applied magnetic field. And the relative permeability is also much greater than 1. So, ferromagnetic substances have properties similar to paramagnetic substances but a little stronger. So their magnetic properties are much more evident than paramagnetic substances, and usually we refer to ferromagnetic substances as magnetic. Now let us learn a little more about ferromagnetic materials. Why do they show strong magnetism? In ferromagnetic materials, there are innumerable number of magnetic domains. What are magnetic domains? Magnetic domains are small regions within the material, and each domain has a volume within 10 raised to minus 12 meter cube to 10 raised to minus 8 meter cube. For each ferromagnetic material like iron, cobalt, nickel, the volume of the magnetic domain may slightly differ. So it will lie within this value. See, it's very small. The volume is small. 10 raised to minus 12 meter cube to 10 raised to minus 8 meter cube. And each of that domain contains 10 raised to 16 to 10 raised to 19 atoms. So there are large number of atoms within the material or within each domain. And within a domain, the magnetic dipoles are aligned in same direction. Here you can see different domains. Within the domain, they are arranged in the same direction. So these are referring to the magnetic dipoles or small molecules or atoms within the material which acts as magnetic dipoles. And they behave like separate magnets because each of them, if you consider a small volume of a magnetic domain which is of this size, you can see that they themselves act as small magnets, but these magnets are arranged in a haphazard way, in a random way, in the absence of a magnetic field. Now, when you place this material in an external magnetic field shown as B naught in this figure, all the magnetic domains get aligned in the direction of this applied magnetic field. So they act as a strong magnet. So in an unmagnetic magnetized ferromagnet, all the magnetic domains exist in a random way. So the overall magnetism is zero. If placed in a magnetic field, the domains arrange themselves in the direction of the magnetic field. In some ferromagnets like soft iron, the domains arrange easily along the applied magnetic field, but once the external field is removed, the domains go back to their random arrangement. Thus, the magnetization is lost. So, certain ferromagnets like soft iron, the it is very easy to magnetize the material. Even with a small applied magnetic field, it gets magnetized. The domains get aligned in the direction of the applied magnetic field. But as soon as we remove the external magnetic field, what happens? They lose their magnetism. They go back to their original state. Now, in some ferromagnets like steel, the soft iron is sometimes called a soft ferromagnet or soft magnetic material because they are easy to be magnetized and they are easily demagnetized, or they easily lose their magnetic property. While some ferromagnets like steel, a powerful external magnet is required to arrange all domains in its direction. But once magnetized, even when the external magnetic field is removed, the magnetism is retained. So they are called hard magnets. It's very difficult to magnetize them, but once they get magnetized, even if we remove the external magnetic field, they will remain as a magnet. So you can guess that the soft iron, which is soft ferromagnet, will be used to make temporary magnets, and the steel, which is hard and which can maintain as a magnet for a longer time, even if we remove the external magnetic field, they will be used to produce permanent magnetic materials. So we have seen why ferromagnetic materials have stronger magnetic properties compared to paramagnets, because within that material, the dipoles exist in small domains called magnetic domains. Okay. Now, let us see the other two kind of materials which are not very common, but yet it is good to learn about them. Antiferromagnetic substances. What are antiferromagnetic substances? The magnetic moments of atoms or molecules align in regular pattern with neighboring spins pointing in opposite direction. So in antiferromagnets, here you can see the picture. In ferromagnet, below Tc, that is below Curie temperature, spins are aligned parallel to the magnetic domain. So here they are all aligned parallel to each other, parallel to the direction of the applied magnetic field below Curie temperature. But in antiferromagnetic materials, even below Tn. What is Tn? Tn is the Néel temperature. When an external field is applied, a small magnetization appears, and above a critical temperature called Néel temperature, the magnetization decreases and it ultimately behaves like a paramagnet. So below Tn, that is when there is magnetic field, the neighboring spins are aligned in opposite direction. So when there is no external magnetic field, the dipoles, each one are arranged in opposite direction in an antiferromagnet. So the net magnetic field is zero. Now suppose we apply a magnetic field upwards. here, an external magnetic field. All those dipoles which are in upward direction will remain so, but those have in the opposite direction, their magnitude will slightly reduce. So there is a small magnetization, a small net magnetization. But above a critical temperature called Néel temperature, it loses its magnetization. So the critical temperature for ferromagnet is usually referred to as Curie temperature, while the critical temperature below above which the antiferromagnetic material does not show any magnetic property are referred to as Néel temperature. That's why it is written Tn here. Below Tn, the spins are aligned anti-parallel in magnetic domains. This is the difference between ferromagnetic and antiferromagnetic material. Now, in ferrimagnetic material, ferrimagnets are like antiferromagnets, except that the magnetization of the two antiparallel atoms or molecules have different magnitudes. This results in a net magnetization. So below Curie temperature, the spins are aligned anti-parallel, but they will not cancel. Why? Because the magnitude of magnetization in one direction will be less than that in the other direction. So they have a net magnetization in the direction of these spins. So as you can see in this figure, upwards there will be more magnetic field, and therefore there is a net magnetization in the upward direction. So this is the case of ferrimagnetic material. And then they have, just for a comparison, shown paramagnetic substances whose spins are randomly oriented at any of the other temperatures. So above critical temperatures like Curie temperature or Néel temperature, they will be completely randomly aligned, and the paramagnetic substance will not show any magnetic property at all. So this is just a comparison. This figure will give you just a comparison of the antiferromagnetic, ferrimagnetic, and ferromagnetic substances. You need not learn in detail about antiferromagnetic substances and ferrimagnetic substances. Of course, you can remember one example for antiferromagnetic substance, which is manganese oxide, and an example for ferrimagnetic substance, that is ferrite. But just remember that in antiferromagnetic substances, the dipole moments are arranged anti-parallel. The neighboring ones exist anti-parallel, so there is no net magnetization. And in ferrimagnetic substances, they are aligned anti-parallel, but the magnitude of magnetization in one direction will be a little less than that in the other direction. So there is a net magnetization. All this is below the critical temperatures. So let us again focus our attention on ferromagnetic substances. So hysteresis, this is a special property exhibited by ferromagnetic substances. We can increase the magnetic field inside a ferromagnet. B represents the magnetic field inside a ferromagnet by applying an external magnetic field. B naught represents an external magnetic field. So we can increase the magnetic field inside a ferromagnet by applying an external magnetic field. Now, when we reduce the external magnetic field, the magnetic field inside the ferromagnet will not reduce in the same way it increased. This apathy for demagnetization is called hysteresis. What is meant by apathy? Apathy means a lack of interest. So the ferromagnetic materials, once they get magnetized, they have no interest in losing their magnetism. This property is called magnetic hysteresis. Now, to learn how this occurs, we usually draw a graph between the applied magnetic field B naught taken along the x-axis and the magnetic field within the ferromagnetic material represented by B along the y-axis. So the graph drawn between the applied magnetic field B naught and the magnetic field inside the ferromagnet B during the magnetization and demagnetization process is called magnetization curve or hysteresis loop. So let us learn in detail about the magnetization, demagnetization process within a ferromagnet. You should learn how to draw this graph and how to explain it, referring to each points which are marked in this curve. So let us start from the origin, O. Here, the ferromagnet is not magnetized. It is not kept in an external magnetic field. We didn't start magnetizing it. So O, at O, the origin, the ferromagnet is not magnetized. So now we are here. Now, we slightly increase the applied magnetic field. So, we increase the applied magnetic field, or we apply a magnetic field. So, the ferromagnet, what happens? Inside the ferromagnet, the magnetic field B slightly increases with the applied magnetic field. So, as we apply the magnetic field, or we increase B naught, B increases, as you can see, along the curve OP. Okay, so when you apply the magnetic field, what happens? The ferromagnet gets magnetized. The magnetic field inside the ferromagnet also will increase until it reaches a point P. At point P, the ferromagnet reaches the saturation point of magnetization, represented by Bs. What happens at the saturation point? We know that a ferromagnetic material is made of a large number of magnetic domains. At the saturation point, all these magnetic domains have aligned in the direction of the applied magnetic field. So there is no more magnetic domain remaining to be aligned in the direction of applied magnetic field. So even if we increase the applied field, there is no effect. It's already saturated. So P represents a stage when the magnetic field, all the domains inside the ferromagnet is aligned in the direction of the applied magnetic field and no more magnetization is possible. So it's represented by Bs. So the magnetic field inside the ferromagnet becomes Bs. Now, let us see what happens when we decrease the applied magnetic field. We expect the material to get demagnetized. So we expect the material to retrace the path through PO, but it doesn't happen. What happens is when we try to reduce the applied magnetic field, or when we try to demagnetize the ferromagnet, the material loses its magnetism slightly and it go along the path PQ. See, at Q, the applied magnetic field B naught is 0, but there still exists some magnetic field within the material of the ferromagnet Br. It is called Br. That is, at Q, though the external applied magnetic field B naught becomes 0, some magnetic field remains in the sample represented by Br. That Br is called remnants or retentivity. That is, the remaining magnetic field inside the ferromagnet even after the applied magnetic field is removed, or the magnetic field retained by the ferromagnet even after removing the applied magnetic field. So what is BR? BR is the remnants or retentivity, that is the magnetic field retained by the ferromagnet even after the applied magnetic field is removed. Also remember, these values of saturation point or remnants will be different for different ferromagnets. Now, in order to demagnetize the material completely, let us see what happens when we apply the magnetic field in the opposite direction. Here you can see that B naught is now applied in the opposite direction, which means B naught is represented by the negative axis, negative x-axis. So it's in this direction. We apply magnetic field now in the opposite direction. When we apply magnetic field in the opposite direction, so the magnetic field inside the ferromagnet gradually decreases until it reaches a point R. So at R, the ferromagnet is completely demagnetized, which means the magnetic field inside the ferromagnet B is equal to 0. The applied magnetic field required in opposite direction to demagnetize the ferromagnet is called coercive force, represented by BC, and BC by mu naught. Mu naught is the permeability in vacuum, is called coercivity, because we have kept this ferromagnet in vacuum and we are applying magnetic field in vacuum, but we are studying what happens within the ferromagnet. So BC is called the coercive force. Coercive force is the magnetic field required in the opposite direction. The applied magnetic field required in the opposite direction in order to demagnetize the ferromagnet completely. Now, once it gets completely demagnetized, let us see what happens when we continue applying the external field in the opposite direction. Here you can see it gets magnetized in the opposite direction, which means the magnetic field inside the material gets increased in the opposite direction, that is along the negative y-axis. So here the magnetic field increases until it reaches the saturation shown by S. Again, the ferromagnet gets magnetized in the opposite direction and reaches its saturation point. Now, when we remove the applied magnetic field, which is applied in the opposite direction, it will retrace or it again loses magnetization in the opposite direction, but not completely. There will be some remaining, as you can see by the point T, where there exists some magnetic field in the opposite direction. And then again, when we increase the magnetic field in the positive direction, again the magnetic field in the negative direction decreases, becomes 0, and again it goes along these paths. So this is the loop that represents the magnetization and demagnetization within a ferromagnet. And this is called the hysteresis loop. So as we said before, when we can increase the magnetic field inside a ferromagnet by applying external field. But when we reduce the external magnetic field, the magnetic field inside the ferromagnet will not reduce in the same way. And this lack of interest for demagnetization for a ferromagnet is called magnetic hysteresis. So in the process of magnetization and demagnetization, some energy is dissipated or lost. The amount of energy dissipated is equal to the area enclosed by the hysteresis loop. See, we have to apply some magnetic field, which means we have to give some energy, and also when we apply the magnetic field in the opposite direction, in all this magnetization, demagnetization process, some energy is lost, and this energy lost can be found out by calculating the area enclosed by this curve. Now, each time we demagnetize and magnetize and demagnetize a ferromagnet, the area will not remain same. The area will gradually reduce each time when we magnetize and magnetize and demagnetize the material. The area becomes lesser and lesser. And finally, it remains a point where the ferromagnet can no longer be magnetized and demagnetized. Okay, I hope the magnetic hysteresis loop and this process is clear to you. If not, please read this again and hear this again, and you should be able to draw the graph and mark the points and explain what is remnants and what is coercivity. So let us continue and see how ferromagnets can be classified based on the shape of this hysteresis loop. Based on the shape of the hysteresis loop, ferromagnets can be classified as soft magnetic material or temporary magnets and hard magnetic material or permanent magnets. In soft magnetic material, as you can see here, the hysteresis loop is thin, while in hard magnetic material, the hysteresis loop is broad, fat. So for soft magnetic material, small coercive force is this distance. Remember? So here the coercivity is very small for soft magnet, which means we do not require a large magnetic field in the opposite direction in order to demagnetize a soft magnetic material. It is easily demagnetized. While a hard material, we need a large applied magnetic field in the opposite direction in order to demagnetize it, or the coercive force is large. So it's very hard to demagnetize a hard magnetic material. Now, example for soft magnetic material is soft iron, hard magnetic material is steel, and it has more retentivity because it gets easily magnetized. It can retain the magnetic field easily, and it has less retentivity because that means it's very hard to magnetize it. We have to apply very strong magnetic field so that it will retain good amount of magnetism. And then it has greater magnetic susceptibility. Greater magnetic susceptibility means easily magnetizable. And for hard magnetic material, lesser magnetic susceptibility means not very easily magnetized. And it has more magnetic permeability. It easily allows magnetic field within the material, while hard magnetic materials have less magnetic permeability. They do not permit magnetic field within it very easily. Now, you can see the magnetic hysteresis curve is thin for a soft material. So, there is less area of hysteresis or less energy loss while we magnetize and demagnetize it. And here for hard magnetic material, more area of hysteresis or more energy loss. That's why we are telling that it's easy to demagnetize and magnetize a soft magnetic material, while it is hard and we have to expend more magnetic energy in order to magnetize a hard magnetic material. Now, soft magnetic materials are used to make temporary magnets or electromagnet. What is an electromagnet? You must have learned that in your grade 10. The magnets that is made by flowing current around it is called electromagnet. Here you can see a picture of a battery and wire connected to it, and the wire is wound around an iron nail. Iron, you know, is a soft magnetic material. So when current flows around this iron, there is magnetic field produced within this, and this iron piece will act as a magnet. Now, once you switch off the current, once you remove this connection with the battery, what happens? The iron will no longer act as a magnet. So it's a temporary magnet, or it is an electromagnet. So electromagnets are magnets that uh, are materials that becomes a magnet when current flows around it, and it will not act as a magnet when current does not flow around it. Now, all these temporary magnets are usually used in electric calling bells, crane. What is a crane? It's used to remove a car, maybe, which has undergone an accident. So when a crane comes, it contains a soft magnetic material or an electromagnet. Now, you will place that material near the car which got damaged and pass current through the material. So it acts as a magnet and it will attract the car. Now, once we take it to the place where it is to be disposed, we can switch off the current. So the crane is no longer a magnet. It will place the car there. So crane uses temporary magnets, and transformer case, the outer case is temporary magnet, and also a telephone diaphragm. The telephone diaphragm should vibrate, so it should be magnetized and demagnetized continuously according to the frequency of our sound. So it should be easily magnetized and demagnetized. So we use a temporary magnet or a soft magnetic material. And armature of generators and motors. What is armature? Armature is the rotating part in a generator or motor. So the rotating part also uses a temporary magnet, while hard magnetic materials are used to make permanent magnets, which are used in the memory tape of a computer. So once it is magnetized, to store that data almost permanently, it should be a permanent magnet or hard magnet. So inside the memory tape of computer, what you have is hard magnetic material. An antenna, which should remain as a magnet for a longer time, and also loudspeaker uses permanent magnets, and the field magnets in generator and motor. You know that in generator and motor, there is a permanent magnetic field represented by north and south pole, which will produce a magnetic field all the time. And inside that, there will be a rotating part. So the rotating part or the armature is made with soft magnetic material, while that permanent magnet that always produce a magnetic field is made with a permanent magnet. So I hope this lesson is clear to you. By this time, you should be able to compare the properties of diamagnets, paramagnets, and ferromagnets. You should just be able to give a sentence or two explaining what is antiferromagnet and what is ferromagnetic substance. You should also be able to explain the magnetic domains within a ferromagnet, and also you should be able to draw the hysteresis loop and define remnants retentivity. And you should be able to compare between soft magnetic material and hard magnetic material, and also tell what is temporary magnet, what is permanent magnet, and where do you use it. Okay, thank you for listening.